Hello, everybody. Nice to see the four of you here.
It's going, John.
Pretty good, pretty good. Happy to be wrapping up this semester. But there's a bit more to go for all of us. Okay. So let me get this going here. See that says microphone off confuses me, but you guys can hear me fine, right?
Yep.
Okay. That is a little strange, but all right. Okay. All right. So welcome to the test 3 review. How can I help you guys? I hope you have some questions prepared. Anybody can go first.
Could we maybe do a brief review over, I guess for lack of a better way to put it, how to recognize which test we need to use? Because like, I mean, I'm good at recognizing ratio, and I'm good at, like recognizing p-series, but when it comes to stuff like, doing limit, limit comparison versus, like other tests, like it throws me off a little bit.
Okay, yeah, that's an excellent yeah, that's a great idea. All right, let me I always got to look up an exhaustive list of all the tests that you've got. So okay. So let's list them all out. So first of all, so here we go. So first of all, you've got some ones like the well, I'll say first, let's say the nth term. The nth term test is useful when the terms don't approach 0. Right, because that's really the only time it tells you anything, right? If you notice that the terms don't seem to be getting closer and closer to 0, well then of course the sum of all of those terms is definitely not getting closer and closer to anything. It is going to be divergent, right? So if the terms are not approaching 0, then you can say if the terms are not approaching 0. I shouldn't say it like that. I'll say if. I'll use this notation instead, which is worse, but I'll still use it anyway. If that is not 0, then of course the series is divergent. And then P series, of course, is when you're looking at something like that or something like that, right? Or anything where it's 1 over n to the something. That's the only time you can use that. And of course, it may not always be written like that. It might be written something like that, but you need only rewrite it as a single power of n. So yeah. Okay. So now for the less simple ones. Oh well, integral tests. The integral test is useful if you know how to integrate that. So for example, if you see something like something like that, right? You know how to integrate something like that, right? That's when it would be a totally good idea. But if you are given something that you don't know, or wait, that wouldn't be a good example. I don't know, something that's like real complicated and you wouldn't know how to integrate, like, you know, n cubed plus sine of n over natural log of n times e to the n or something like that, right? If you were to switch this out for this, like, good luck, you know, you got to figure out the antiderivative of that, right? So this is a good idea. That is a bad idea, right? It's literally just, you know, if you swap it for an integral, do you know how to handle that integral? So yeah. All right. Comparison test, right? So the comparison test, sometimes called the direct comparison test, is useful if you can clearly see that these terms, so I'll say it in plain English and I'll say it a little more precisely in a minute, that these terms are always bigger than those terms. Right, so for example, something like that, right? That's not a p-series, and so you would not be able to use the p-series test, but you could probably compare it to this. And since you know, it's clear, it's very simple, right? The only difference between them is the +1. So it's clear to see that these terms have bigger denominators, which means that each of these terms is smaller than each of these terms. So definitely then the sum of the series would be smaller. And since you know that this one is convergent, well, that tells you that since this one's smaller, it must also be convergent. So that's quite a useful test, but that's only useful if it is super simple to see that these terms are always smaller than those terms, you know? So an example where it would not be useful would be, say, if it was more like this. Well, I'll say something like n plus 5 over n cubed plus 1, and compare that to 1 over n cubed, right? Well, now it's not really, now the direct comparison test is not useful anymore because, you know, you can't simply say, well, that's always bigger than that. Well, it's not true, because while it does, this one has a bigger denominator, which indeed makes these terms smaller. Well, it's also got a bigger numerator, which would make these terms bigger. And so it's unclear which of those effects is going to win out. And it's unclear, you know, whether sometimes these terms might be bigger than those, but maybe sometimes those terms are bigger than that, depending on where in the series you look. It's not always the case that those are bigger than those. So you can't simply use the direct comparison test in that case. But that's where the limit comparison test comes in handy. So where the direct comparison test fails, if you can't simply say, well, those are always bigger than those, so that's that. Well, you might still be able to compare them using the limit comparison. So instead of just simply saying, oh, well, that's always bigger or that's always bigger, instead, you take the limit of their ratio. So the limit of their ratio, and you take that limit, and it works out to be, oh, wait. Well, so in this case, so what I've chosen here in this case, I choose this limit and it gives me infinity, right? Which more or less means that the limit comparison test is inconclusive. So that would not be the wise choice to compare it to, right? And the reason it gives me infinity, of course, is because when I simplify this out, I end up with a 4th degree polynomial over a 3rd degree polynomial. And so that works out to, it's at infinity, it's pretty much the same as this, which is pretty much the same as that, which goes to infinity. So that's actually inconclusive on the limit comparison test, right? When you do the limit comparison test, you want the limit to work out to be a number, a constant number. And then you can say that the two series are of the same power level. So perhaps instead of 1 over n cubed, what I really should have compared it to was 1 over n squared, right? If I were to compare it to 1 over n squared instead, then it would change this whole thing here. Oh, I screwed that up, actually. That was supposed to be 5n cubed, but whatever. If I did 1 over n squared, then these would end up being the same power level. They would both be n cubed, and that would be 1. And so that would purchase 1. And so the limit comparison test would tell me that these two series are of the same power level. They do the same thing. They either both converge or both diverge. And since the p-series test tells me that this is convergent, then that tells me that this one also is convergent. So to answer the question, the direct comparison test is when you can directly compare their sizes. You can say, well, these terms are always bigger than those terms, and so if that one's bigger than that one, and that one, I should say a little more about that. If you're using the direct comparison test and you can see that these terms are always bigger or always smaller than these terms, and you know that this series converges, well, then that tells you that this series converges as well because it's smaller, right? If this is finite and that one's smaller, well, then it's also finite. But be warned, if you know that that series is always smaller than that one, and you know that this one diverges, well, then you know nothing about the first one, because it might, if it's smaller than infinity, it might be finite, or it might just be a smaller infinity, and there's no way to tell. So you gotta watch out for that. Similarly, if say you know the other thing, if you know that that series is always bigger than this other one, and you know that this one is convergent, well, that doesn't tell you anything. If it's bigger, well, it might just be a bigger but finite number, or it might actually be infinite, and you can't tell the difference. However, if you know that this one diverges and you know that that one's bigger, well, then you know for sure that it's got to diverge, right? If it's bigger than infinity, it's got to be infinity. So yeah, so that's the direct comparison test, but that's only useful if you can actually just set a hard answer to which one's bigger in every term. If you can't do that, then the direct comparison test is not going to work. You might try instead the limit comparison test. You might be able to get a certain limit of a ratio to work out to be a nice constant, and then you can say confidently that those two series are of the same power level. Yeah. Is this helpful so far? Is this the sort of thing that you were looking for?
Yes, thank you.
Okay, you're welcome. If you want me to take it in a certain direction, let me know.
No, actually, can we do the alternating series as well?
Absolutely. So the alternating, okay, so let me actually, okay, hold on. So let me actually go back to the nth term test, right? So the nth term test, recall, says if the terms are approaching 0, if the terms are not approaching, well, if the terms are not approaching 0, then the sum of those terms diverges, right? And I hope that makes sense, because in the end, when you're adding on the infinitely many terms at the end of the series, if they're not all 0, then you're adding infinitely many of something, and that's going to be infinite in the end. So of course that diverges. The only way it has a shot of converging is if the terms are actually approaching zero. But that alone is not enough to say that it for sure converges. Right, so in other words, if the terms are approaching zero, then the nth term test is inconclusive, right? Which is why it's a very weak test that you learn early on. That's only helpful, occasionally. And of course, a classic example of that would be the harmonic series, right? Of course, the individual terms are approaching zero, but that alone is not enough to mean it converges, right? It in fact diverges despite the terms approaching zero, right? Okay, so I've mentioned that because the alternating series test is really quite similar. The alternating series test is a lot like the nth term test. It says if these things are not approaching zero, then the alternating version of that series diverges, right? So it's just like the nth term test in this case. Now I say alternating version, I did it with a -1 to the n, but it could be -1 to the n plus 1 or n minus 1 or whatever, or even some other weird stuff. Anything that outputs 1, -1, 1, -1, in some order, it doesn't even matter. Just anything that makes it alternate, right? So it doesn't really matter how you notate the alternating situation. -1 to the n is a classic, but it could be all sorts of things. It's just the point is that the terms some of them are negative and some of them are positive, right? So yeah, so alternating series test, this part is exactly the same. If the terms themselves are not approaching zero, then it definitely diverges. But the alternating series test is more powerful than the nth term test. Its weakness is that it only applies to alternating series. But if you're talking about alternating series, it is more powerful. It says if those terms are approaching zero, then you can say that this 100% converges. It is not inconclusive. So that is to say that if the terms of an alternating series are approaching zero, that alone is enough to conclude that the series is convergent, right? So different from the non-alternating case, right? And the important example is that while this series, the terms do approach zero and yet it is divergent, right? In this case, if you take the same series, but you make it alternating, right? This is actually convergent, right? The terms are approaching zero, 1 over n goes to zero. And the fact that this is alternating means that the alternating series test says that this is convergent. And the sum doesn't matter, but just for what it's worth, it converges to that. So yeah. What I want to put in your heads is that the alternating series test is kind of like a more powerful version of the nth term test, but it only applies to alternating series. So when should you use the alternating series test? Well, of course, for alternating series. You should use the alternating series test if your terms are alternating, meaning that half of them are negative, half of them are positive. And again, there's lots of ways to construct an alternating expression. This is probably the classic way where you have something like this, but there's lots of things which perform that same role, right? Another classic would be something like that, right? If you plug in, 1, 2, 3, 4 for n, that's going to be +1, -1, +1, -1, right? So there's more than one way to notate an alternating situation. really you just gotta get in there and inspect, are the terms plus minus, or are they all plus, you know? So yeah, so if your terms, some of them are positive, some of them are negative, and it is easy to take the limit. That is when you should use the alternating series test. So for example, something like that, right? If it's easy to take the limit of the rest of it, so you could ignore the alternating portion, but if you take that limit and you see that that goes to 0, then that instantly means that it converges, right? So unlike the nth term test, where if you see that the terms go to 0, that doesn't tell you anything. In the case of alternating series, that's enough. That means that it converges right then and there. So you just have to check that the terms are going to 0, and that means that it converges if it's alternating. So yeah, that is when you should use the alternating series test. Man, this coffee is nasty. Did I not clean out the thing enough? Maybe I didn't. That sucks. Okay. Okay, so there's only a couple more to go. So let's talk about the root test, because that one's got a if there is an nth power to cancel to cancel with your nth root. Right, so root test is useful for something like this, where it's, I don't know, 2 over n plus 1 or whatever the hell you got, all to the power of n or something like that, right? It is a good idea to use the root test on something like that, because then you're looking at the limit as n goes to infinity of the nth root of 2 over n plus 1 to the n, and those things cancel each other. So that is a good idea. That is a totally good idea to use the root test. It would be a bad idea, arguably, to use the root test on something like that, for example, where it doesn't exactly cancel. Well, let me go a little bit further here. Right, it simply cancels with the whole thing, right? Whereas in this case, you might be able to cancel it on the top, but then you've still got this strange thing on the bottom. So it's kind of a weird limit. So this is a good idea. This is maybe an okay idea because it kind of cancels it, but you still have a difficult limit to figure out. I don't know if you know how to find the limit of the nth root of n plus 1. It's kind of a strange limit to take. If you can handle that, then great, then it's a good idea, but still it's not as much of a good idea as it was when the whole thing canceled. And then if there's no nth powers at all, if it's like, that or something, right? Well, then that's a terrible idea, because now you're looking at something just absolutely horrible. Good luck taking the limit of the nth root of that. That is a bad idea. Right, so of course the root test applies in all cases, but it's only useful if it actually cancels with an nth power. So yep, that's when you should use the root tests. And then lastly, the ratio tests. It's a good idea it's basically just a good idea if you can take the limit of the ratio. Right, so if you work out, if you get to a limit that you can actually work out that way, then it's a good idea to use the ratio test, which might seem like kind of a cop-out answer, but that really is what it comes down to. So I'll just put in parentheses, often useful if there are factorials involved, or so stuff like you know, I don't know, n factorial over 3 to the n times n or something like that, right? That would be an excellent time to use the ratio test, would be something like that. But you know, there's exceptions. It really just comes down to whether you can take the limit. So you really kind of just got to work it out and see. But it, you know, it's a useful guide. If there's factorials and exponentials, it's probably the move to use the ratio test. Often it is not useful, and again, there's exceptions, but often it is not useful if there are multiple terms. You know what, honestly, a better way to say that, I should say if there is addition or subtraction, right? So if you're looking at something like n factorial plus 2 to the n over 3 to the n, right? I probably would not recommend the ratio test on a series like that, because you're not going to be able to, the limiter is not going to cancel out as nicely, right? Because on the first one, if you do the ratio test, it's going to be something like this times the inverse or the reciprocal of right? And then you're going to be able to do all this cancellation, right? 3 to the n cancels with that, leaving a 3. N factorial cancels with this, leaving an n plus 1, and so on. So you can do all this nice stuff. But if it's like that, well then, geez, it's not quite as nice anymore because not everybody's multiplied together, you know? So that plus is really, plus 1, that plus is really screwing us up, you know? Right, you can't just be like, oh, that cancels with that, leaving a 2. No, because they're not simply multiplied together, you know? This plus of this other thing totally messes that up. So you won't be able to algebraically simplify it as nicely. You might still be able to come up with a way to take the limit, but it's going to be quite difficult. I would not recommend that. So yeah, generally speaking, and emphasis on the generally speaking, if all you got is like a bunch of stuff like this multiplied and divided together, then it's quite easy to simplify that when you do the ratio test. If you've got multiple terms of any kind, it's usually quite difficult to work with that when you do the ratio test. So yeah, that's what I'd say is usually the situation. Okay. So I think that's about all of them. So let's head back here for a second. What the heck? Stop. So yeah, so nth term is useful if the terms are not approaching 0, and it's easy to see that. P series is only if it's a P series. Integral is if you can take the integral. Direct comparison is if you can see that, you know, the terms of a different series, which you do know the convergence or divergence of, are clearly bigger or smaller than the terms of your series. And then you can, you know, simply say, well, okay, so my series must be smaller than that one. And since I know that one converges, then I'm good to go. Or something like that, right? Maybe, you know, my series is bigger than that one, and I can see that that one diverges, so then mine also diverges, right? But you got to be careful about getting it in the wrong order, right? If my series is smaller than that one, and that one diverges, well, that doesn't tell me anything, right? So you got to be careful about the direction there. I hope that makes sense. I can elaborate on that if you request. Limit comparison is pretty much if direct comparison doesn't work, more or less, you should try the limit comparison. It's especially useful for ones like this, where it's a rational function, where it's a polynomial. Whoops, oh shoot, that's not what I meant to do, where it's a polynomial over another polynomial, it's often a good idea. In fact, I might even say always a good idea to do the limit comparison between your series and a p series. And you choose the p series such that the, sort of total degree matches between both. That way, when you take the limit, it works out to be a constant, and then you can actually use the limit comparison test. Yep. Alternating series is useful if the terms are alternating and the terms are going to zero. In fact, actually, I said no, actually that's not true. It's useful to use the alternating series test if the terms are alternating and you can take the limit. It doesn't matter if it goes to zero or not. That the alternating series test just straight up immediately tells you the answer if you can take the limit at all, which is super useful. So yeah. And of course, again, compare that to the weaker nth term test, which if it's not an alternating series and you find out that the terms are approaching zero, that's inconclusive. Whereas if it is an alternating series, that is conclusive. It tells you it converges right there. So yeah. Okay, and then the root test is only useful if there's an nth power to cancel. And then the ratio is only useful if you can actually simplify the ratio, is pretty much what it comes down to. So yeah, I'd say that's when you should use these tests. I wonder if there's a way for me to output this. Oh, there is. I'll probably post this then. Okay, what do you think?
Looks good, thank you.
Okay, cool. Participant 6. Okay. So yeah, so we just did kind of a general overview of all the different tests and when you should try each one. Welcome, Fahad. Oh, there's stuff in the chat. Yes, Cheno. So all the tests apply all the time, pretty much. I mean, like the alternating series test only applies to alternating. But besides that, they pretty much all apply. Like you can always use the integral test if you wish. You can always use the root test if you wish. You can always use the ratio test if you wish. It's just that when you attempt to do so, you might end up with a limit that's like totally impossible to take. And then it's like, damn, okay, I guess I should do a different one. So yeah, so many of the tests are applicable always, but are only useful sometimes. And you just kind of have to, go into it to see, when that's the case. Okay, so Brian asks, find a power series representation of that function.
For some reason, I'm having an easier time with Taylor and Maclaurin than just a regular power series.
What is the difference between those?
Well, the Taylor and the Maclaurin are kind of special cases, centered at zero or centered at a specific number. Power series doesn't center at any spot, does it?
No. So power series. So Well. So what? So now. Well. Calling it Taylor or Maclaurin series really just kind of refers to the way that you came up with it, I guess, because it's still a power series. So yeah, so if you have a well, I guess it refers to if it's equal to a function or not. So yeah, so any infinite polynomial is called a power series, and it may happen to be the Taylor series of a particular function. It may not. So yeah, so in this case, when they say find the power series representation of that function, one totally valid way of answering that question is to simply use the Maclaurin series formula on that function. And then, yeah. And so you can get the, Taylor series that way or Maclaurin series that way. And that would be totally legit. However, using the Taylor series formula is easier said than done, right? The Taylor series formula. See, I wish I got this thing because it advertised like infinite zoom, but it's not that. It's I was swindled. Can I change the size? Yes. So yeah, so a function has a power series like this, right? If I were to focus on centered at 0, right? It's this, right? It's an infinite polynomial sum of a bunch of different powers of x where the coefficients are this, right? And it depends on the function naturally. To do it this way, you'd have to take an infinite sequence of derivatives of your function and then plug in 0 into all of them. Now, I don't know about you, but taking infinitely many derivatives of this guy doesn't seem like that much fun. So yeah, let's not do that. Infinitely many derivatives of that, right? Because the very first one's going to be a quotient rule. The next one's going to be even worse than that. It's just going to be a disaster to do it that way. But you could do it that way. It is 100% the exact same thing. A power series and Maclaurin series are the exact same thing. So if you were to do it this way, you would get the right answer. It would just take you a very long time. So instead, there's another technique that you can use.
So if the differentiation is ugly, you don't want to go down those paths.
Yes,
Gotcha.
but it would be totally valid to do it that way. So the trick is start. So I hope you know this power series, that the sum of just the powers of x. So all the coefficients are 1, right? So meaning etc. Right? I hope it is familiar to you that this is equal to this nice function. Is that familiar?
Yep. And
as long as you're within the interval of convergence, right? So as long as x is between -1 and +1, right? So of course, if x is 2, then that's 1 + 2 + 4 + 8 + 16 + 32, which obviously diverges and is certainly not equal to 1/1 - 2. But yeah. But as long as you're within that interval of convergence, then those two things are equal. So that is the power series. So yeah, so you could call this series over here the power series for 1/1 - x. You could call it the Maclaurin series for 1/1 - x, or you could call it the Taylor series centered at 0 for 1/1 - x. Those are all exactly the same thing. So we want to get from here to let me see what it was again. X over 1 + 5x squared. Okay, so the idea is let's see if we can manipulate this thing on the left to turn it into that. And our manipulations, we can we can take derivatives, we can multiply by x's, we can divide by x's, we can substitute x for a different thing. We can do all kinds of things to that. And as long as we do those exact same manipulations to the power series, then we should be able to keep them equivalent the whole time. And then when we're done, we'll know the power series for that function. So that's the idea. So let's actually start over here. So I'll write it like this. So here's our starting line. And we know that this is equal to this power series. Nope. This power series, perhaps the simplest power series that there is, where they're all 1s. All the coefficients are 1s, I should say. That's probably a little much. Let's stop right there. And I'll also write it in sigma notation over here, just so that we're keeping up with that. Okay, so we want to get from here to here. Okay. So a couple things are different between this one and this one, right? But you can see it's almost the same. It's not completely different, right? It's not like sine of x or e to the x or something. It's like it's a very similar type of thing, but it does have some key differences. Key difference number one is that there's an x in the numerator, right? Well, that's very easy to handle. We'll simply multiply by x to get an x in the numerator, and multiplying by x in a power series is also very easy. You simply distribute it in, and so all the powers go up by 1, right? So that's very easy to do. Okay, so we know how to make that part happen. The other part is there's a square, right? The denominator is squared. So one way that we could attempt to make that happen is simply square both sides. Then it would become 1 minus x squared, and we're a little closer to what we want down there. But that would be a horrible idea because we would have to square this infinite polynomial. Now, I don't know if you've ever attempted to FOIL two infinite polynomials together, but it's quite difficult because, you know, if you have to multiply this by itself, well, you have to take this first term and multiply it by all of these. And once you're done with that, which you never will be, then you have to take this term and multiply it by all of these. And once you're done with that, then you have to take this term and multiply it by all. So there's infinitely many, infinitely long things you got to do, which is quite difficult. So it's very difficult to do it that way. So we won't do that. We will produce that second power another way. The other way to produce a second power in the denominator is to take the derivative. Right? What would be the derivative of that function? Well, it's 1 minus x to the negative 1. So that means the derivative would be negative 1 times 1 minus x to the negative 2, But then the chain rule says times the derivative of the inside, which would be negative 1. So that's super nice. It cancels with that. So yes, so it seems that taking the derivative has the exact same effect as squaring. And that's absolutely fantastic because I do know how to take the derivative of this infinite series. It's actually quite easy. That's 0, that's 1, that's 2x, that's 3x squared, and so on, right? So it's actually quite easy to take the derivative of both sides rather than squaring both sides. And then just to continue on here, it's also quite easy to take the derivative even in sigma notation, because for every single one of these terms, regardless of the value of n, what you do is the n comes down and multiplies out front, and then the power subtracts. So for every single one of those terms, it's like that. And indeed, you can check that if you plug in, you know, n equals 0, or that's 0, or you know, it'd be 0 times. Well, some people don't like that because of the first term. Don't worry about that though. That's not really, that's beside the point. So, you know, if you plug in 0, 1, 2, 3, right? I hope you see how this expression gives you these 4 things, right? So taking the derivative even inside the sigma notation is totally legitimate, which is super cool. You just treat the n as a variable because it is, and then you just you know, go through it like that. So yeah, so I do want to add, some people don't like what's going on with this first term here, because they say when you plug in n equals 0, it's really, you know, 0 times x to the negative 1, and negative 1 is sometimes undefined, so that's kind of like a problem at that, you know, whatever. That's kind of, in my opinion, a little too much technical detail that kind of distracts from what's really going on. But if you are concerned about that kind of thing, you can simply ignore the first term by just starting it at 1. So yeah, you can avoid that problem if you wish by doing that. Okay, so we are getting a little bit closer here. We've got the second power that we need, but there's still two more things that we need to do. One thing is this what is currently a negative x needs to swap out for a positive 5x. And then also this numerator needs to gain an x, right? So gaining an x is quite easy to do. We simply multiply the whole series by x, so that's very simple. I'll leave that for the end. Let's deal with this part first, right? So here's a cool trick you can do. You can simply replace your input with literally any expression in the entire universe, and that will be totally legit. So if I wanted to, I could replace this with tan of x, and I would get, 1 over 1 minus tan of x squared equals 0 plus 1 plus 2 tan of x plus 3 tan of x squared plus 4 tan of x cubed, and so on. And that would be 100% legit. So that's pretty cool. But in our case, we don't want to replace it with tan of x. We want to replace it with negative 5x, right? Because if we replace that x with negative 5x, then 1 minus x becomes 1 minus negative 5x. And that's precisely what we want, right? Because that's 1 plus 5x. So now we merely need to do the same thing in the series. I won't write the 0. I'll just write the 1. So 1 plus, and then instead of 2x, I'll say 2 times negative 5x. And then instead of 3 times x squared, it's 3 times negative 5x squared. And then the next term, instead of being 4x cubed, it's 4 negative 5x cubed, and so on. And so indeed, it's quite easy to do in the sigma notation as well. You literally just replace the x with negative 5x. So it's n times negative 5x to the n minus 1. Okay. And then finally, there's one last thing we need to do to turn that into that, which is multiply by x. So give everything just one more x. So that's going to be 1 plus. So if you want to, you can work out these coefficients if you want. That'd be 1, and then I suppose that would be negative 10x. But now we're giving it an extra, so that's 10x squared. You know what? I won't do it that way. I'll just write it out. Hold on. Let me write it out like that up here. So if you wanted to, you can work out these coefficients to get like exactly what they are, Wait, no. And so on, right? So if we multiply that by x, well, then now it's going to be x minus, I'm glad I did that because I screwed it up, 10x squared plus 75x cubed minus 500x to the 4 plus, and so on. And so if you wanted this thing in general in the sigma notation, let's see if we could maybe simplify this a little bit. I mean, one thing you could do is you could take this exponent and distribute it inside that multiplication, right? Recall, let me just say something. Recall that exponentiation does distribute over multiplication. That is 100% legit. And also, multiplication distributes over addition. That is totally legit. But it is very important to know that exponentiation does not distribute over addition or subtraction, for that matter. That is very, very important. A lot of people made that mistake on the last exam. So yeah, just know that. Okay, so anyway, but it does work over multiplication. So we can simplify this like this. So far I haven't done the next step. I've just rewritten it, right? Those are equivalent. But now that I multiply the whole thing by x, well, it's literally just multiply this by x. So of course, this is going to go up by 1. So now it's n negative 5 to the n minus 1 times x to the n. And there you have it. So this infinite polynomial, also expressible like that, is the power series for this function, right? So we could have gotten that with Taylor series. We could have gotten that by taking, a bunch of derivatives and plugging that all into this formula. That would be totally legit, but that would have taken ages. The other way to do it is to come up with a sequence of, things that you can do to usually to this one. Usually this is the one that you start with. Come up with a sequence of things you can do to that to turn it into the thing you want, and then you do that same sequence of things to the power series, and then that will get you the power series.
Hey, John, that was great. Quick question. When you went from the first 2 steps there, when you took the derivative,
Yeah.
your summation went starting at 0 to starting at 1. That keeps throwing me off when those things happen.
In my opinion, that's a silly technicality that we needn't worry about. But I suspect that in Dr. Teodorescu's opinion, that's going to. But I'm grading the exam. Okay, so never mind. Never mind. You don't even worry about that. The only reason that's like a technical problem is because this is totally well defined for all x, no problem. You're not dividing by 0 or anything, because you don't have any negative powers of x, right? This, the sum from x to the n, right? There's no negative powers of x in there, so no problem. That's perfectly well defined everywhere. But if I say this, the first term is that, right? It's a negative power of x. Which means that if you were to plug in x equals 0, it would be a weird undefined thing. So
okay, so
literally,
the only reason you did that is to keep that anomaly out of the equation.
Exactly right. Exactly right. So yeah, so it's just a little slight adjustment to avoid like a technical problem. But frankly, it's kind of a technical problem that you should feel free to just ignore anyway, if you ask me. So it's kind of whatever. I certainly won't make a big deal out of it. If you and personally, when I'm personally messing with power series, I don't. I just leave the thing the same because it's better that way.
Okay, so what you mentioned a minute ago is that you're going to be grading the tests. He sent out a notice today that the test will be online.
Yeah.
Through WebAssign, and then we have to email to his email address, I guess, our work. So I just want to confirm that you're definitely grading the test, because you guys have different philosophies. Last time I put a lot of detail into it thinking he was grading it, and then find out you were grading it, and I could have probably saved a lot of time because I ran out of time. I'm not going as detailed.
As far as I know, I am grading the exam, and I would be pretty surprised. I mean, unless it's being graded automatically by WebAssign, which I don't believe it is.
Okay.
Right?
Don't know.
I mean, if you're
this
emailing,
this situation is kind of new for everybody. So on the chat, everybody was kind of blowing up the chat, wondering what's going on.
Oh man, yeah. Well, as far as I know, that's what's up. Is he's probably, so my guess is that he's gonna send it to me, and then I'm gonna either print them all out or probably just do it on on the computer. So yeah, so probably I'm the one grading it, but I'm not 100% sure. I guess you should ask him if you want to know for sure. Yeah, so I don't know at the moment.
Okay.
I would guess with like, 90% confidence at least that I'm going to be the one grading it, but I'm not 100% sure. So let me just, I gotta do this real quick. Let's just take a look at this function. That looks like this. Wow, funky. I'm gonna sort of give it a, no, whatever, that scale's fine. Okay, so that's what that looks like. Let's take a look at the power series, which we said was n times, well, I'll just start typing it actually. X minus 10x squared plus 75x cubed. Ooh, see that? See how on a tiny window that's looking like absolutely identical, but if you look a little further, then it's not. Minus 500x to the 4. Ooh, even better, right? So yeah, so it looks like this is the correct power series. However, it looks like it might have a rather tiny interval of convergence, right? It might only match on a rather small section around 0, right? It should be centered around 0 because it's a Maclaurin series. All of the powers are of x rather than like, x minus 2 or whatever. So it is centered around 0. But it looks like the interval of convergence doesn't go very far. In fact, I suspect it should only go 1/5, but I'm not sure. So let's also write out the sigma notation so we can get a lot more terms. The sum from n equals 0 to a lot of n times -5 to the n, come on, n minus 1 times x to the n. Ooh, oh baby, look at that. So look just how utterly perfect that is, right? So there you go. That is the power series of that, But yeah, it only matches on a small interval. I suspect that interval is -1/5 to +1/5. You could deduce that.
That's correct.
Yeah. Okay. Yeah. So you can see how the close, in this case, it's diverges away from it prior to 0.2, but that's because I only went 20 terms. If I actually went like a lot, like let me try like 50 terms. Yeah, so the more terms I add, the closer it gets to the 0.2. If I truly had infinitely many terms, then it would be like a sharp turn right there. It would exactly match all the way up to exactly 0.2, and then immediately after that, it would start diverging instead. So yeah. So anyway, you can see how beautifully these align, right? At least on the interval convergence. So yes, this is the power series for that function.
Well, that gives meaning now to convergence and divergence so much more now, actually, with the graph.
Awesome. Yeah. Gotta love the graph. The graph is absolutely the best. And then another good one to just sort of be familiar with is this one, right? This is literally just simply the powers of x, right? And you can see it sort of has this nice curve to it, and then it suddenly kind of changes direction. That's because the interval of convergence ends at -1, right? This is actually 1 over 1 minus x. And you can see how those completely align on the interval of convergence, but then as soon as you get to the edge of that interval, it shoots off because it no longer converges for those values of x. So yeah. Okay. All right. You're welcome, Lauren. Goodbye. Okay. All right. So that was that. I hope that made sense, Brian.
Yeah. Yes, thanks.
What is next? Anybody else? Who do we got here? Can I help you guys with anything? Fahad or Darren or Jenna?
Darren just posted something in the chat.
Oh, thanks. General question. When you want to increase or decrease the series, like change the terms from n equals 0. Okay, so I think you're talking about re-indexing. If I'm understanding your correctly, you're saying if you have a series like I don't know, let's say like 1, well, Yeah, sure. Like a half plus 5 over 4, 5x over 4 plus 25x squared over 6 plus 125x cubed over 8 plus 625x to the 4 over 10, right? So if you're trying to find a, sigma description of this infinite series, I don't remember the next one, I think it's this. Right? So of course the trick is to come up with the pattern, right? So you see the numerator is, powers of 5 and powers of x, and the denominator seems to be even numbers. So, but how do you describe it exactly, right? One option would be to say, well, let's call this the n equals 0 term, n equals 1 term, n equals 2 term, n equals 3 term. If you were to go with this description, you might call it, you might say, well, the numerator seems to be powers of 5 in powers of x, right? Where the actual power matches n in that case. And then the denominator is even numbers, so I might try 2n, but that doesn't quite work because 2n here would be 4, not 6, and 2n here would be 8, not 10. So actually you gotta bump it up by 2 in order for that to work, right? Now when you plug in 0, that's 2, you plug in 1, that's 4, you plug in 2, that's 6, and so on. But that's just one way that you could have described it. You could have equally well said, okay, let's call this the first term, and therefore this is the second term, and therefore this is the third term, and therefore this is the fourth term, and so on. Well, if you call it that way, then you say, well, okay, you're starting at 1 to infinity. So this time the denominator is very nicely just 2n, because that's 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. So that's nice. But the numerator now isn't quite as nice because 5 to the 1 would be 5, not 1, and 5 to the 2 would be 25, not 5. So those are now off by 1 from the nice version that they were last time. So if you want it to work out, well, then you just got to subtract 1 from each of these, right? Now the left one I actually want to write in a slightly different way so that I can illustrate something. Rather than writing it as 2n plus 2, you can think of it like this as well, right? So so both of these series, and let me even do one more. If I wanted to, if this would be absurd, but if I wanted to, I could say, let's start this at 7. Could, totally valid to do that if you want, if you're nuts. Okay, sum from 7 to infinity. Well, what's the deal? Well, in the denominator, I first have to get down to 1, and then I'll multiply by 2. And then in the numerator, I basically got to go down by 7 for that to work. So all of these different descriptions are 100% legit. Those are all descriptions of the exact same series, but their index starts at a different value. And consequently, you have to kind of shift the ends by this or that to get them to line up, because they all, when you plug in the first term, they all got to work out to be 1/2 some way or another. And when you plug in the next term, they all got to work out to be 5x over 4, So the way to, so let's say, I think this might more directly answer your question. Let's say you started with this and you wanted to rewrite it with an n equals 1. Well, you just got to shift all the ends, right? So you got to move this down by 1. Well, you got to move them all down by 1. So move these down by 1 as well, which is going to, end up subtracting by 1 like that. And indeed, if you shift by 7, you got to move down by 7, and so on. Personally, when I am working with series and have to think through like a confusing thing like that, like a change of index, personally, I always write out the first couple terms of the series in full rather than trying to work with it entirely in sigma notation, because it's just so compact. It's kind of hard to tell what's going on sometimes for me. So personally, I like, if I were given this, I would sit down and be like, okay, so plug in 0, that's 5 to the 0, x to the 0 over 2 times 1. So that's 1/2. Next, plug in 1. That's 5 to the 1, x to the 1 over 2 times 2. So that's 5x over 4, and so on. And then if I have to reindex, I would say, okay, so actually I want this to be 1 and this to be 2. So then how do I make that happen? Well, and I sort of work through it that way. So I would definitely write out the first couple terms, at least as a just to check yourself, because it's quite easy to, at least I find it quite easy to screw stuff up if I stay entirely in sigma notation. Did that answer your question, Darren, or was that not quite what you were asking? Man, this has been here for an hour. I hope it's still good. It's okay. Awesome, Martin. I'm glad that's over. Okay. Anybody else? And Brian, in my message, I was like, everybody should talk, but those who do talk a lot, such as you, I'm not discouraging you. Please, I appreciate your interaction.
Yeah, I didn't take it personally.
Okay. All right. Good. Okay. So, Jeno or Fahad, do you have anything I can help you with? And if not, then Darren or Brian, feel free to ask me another question. I will be right back. Okay, I'm back. All right, awesome. Okay, Fahad says power series of ln of x 6 minus x. I came late, not sure if you did that already. We have not done that exact problem. Fahad, were you there for when we did the other power series question? And okay, great. So it's actually quite similar to that. Well, hang on a second. Wait a second. Let me think for a second. Does it specify where to center the power series around? Does it say 0, or does it let it be somewhere else? Man, that would be so just feel like if it doesn't specify, then you can probably do wherever you want. So Fahad, does it start with the same? Does it start with the same thing here? because that's what's coming to mind for me, is that perhaps we can do the same sort of trick where we start with this one and then we manipulate it until it looks like the thing that you're looking at. Natural log of 6 minus, I'm already back at max zoom, dude. Are you kidding me? Jeez. Ugh, what a mess. What a mess. All right, zoom way in here. 1 over 1 minus x is equal to the sum of the powers of x, which is super cool. Gotta love that one. That's probably, it's got to be one of my favorite power series because it's just so simple and so nice. And it's one that you, whatever, it doesn't matter. I shouldn't go on and on about it. Okay, it starts by getting the derivative of it and then integrating it. Well, why would it do the derivative? If it does the derivative and then the integral, then it's just back to where it started. Right? Because those are opposites. So the 6 minus x. And then the other thing I want to ask Fahad, if you're looking at the answer key there, does it end up with a power series that looks like this, like where it's powers of x? So blah, 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 x to the 4, blah, 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 x to the 5. Or in sigma notation, it would be like blah, 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 x to the n. Or does it look more like, let's see, it would be, 6 minus x. So what am I thinking? Minus x minus 5. So yeah, or does it look more like this? X minus 5 cubed plus blah, 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 x minus 5 to the 4 plus blah, 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 blah. And in sigma notation, it would be blah, 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 x minus 5 to the n. That's what I mean by asking, is it centered at 0 or is it centered at somewhere else? Because if you're allowed to center it somewhere else, then I have a nice thing we can do to pretty quickly turn it into that. If we have to center it at 0, then we'd have to be a little more tricky to get that 6. Fahad?
This is Brian. I'm reading it because this was the question on the homework. This was like a 7-step process where, yeah, it's very convoluted. At first, it says recognizing that the function is an antiderivative. To find this, we find the derivative of it, and then they take the integral of it, I guess, to find c, and with the goal of finding c. So, if you have an easier way, I'd be happy to hear it.
Oh, I see. So starting with this, taking the integral of that. It's taking the derivative of that.
Right. They take the derivative of that to get negative 1 over 6 minus x.
Right. But then.
And then they say based on that, if you take the integral of negative 1 over 6 minus x, you get back to ln 6 minus x plus c.
Right. So it must be that c was actually 0 in order for it to equal this thing that we started with. Right?
Well, then it says, then in step 3, it says our goal is to find a power series for minus 1 over 6 minus x, and then integrate it.
Right. Right. Yeah, exactly. So let's work with this one instead, and then we'll handle the so that 6 is really, really, really messing us up because we know how to work with this, right? 1 minus x. Now we have this technique you can do, right? You can like I said before, you can replace x with anything else. So for example, I could replace x with like, with like, 13x if I wanted to, right? I could say this is, 1 over 1 minus 13x. I could say that if I wanted to. So I can easily get a different coefficient here, but it's quite hard to get a different coefficient here, but it can be done. Here's how I would do it. If I'm trying to get a 6 there, I would give it one of these. Replace x with 1/6 x. So now it looks like this. Or you say x over 6 if you prefer. But now I can simplify this expression by giving it a times 6 over 6. Because after that, I can distribute the 6 across the denominator, and I end up with that, which is only a constant multiple away from what we were looking for. So yeah, so that will do the trick. That's how we can get that 6 minus x. We don't have to do the the other thing that I was thinking was replace let's see, what the hell would it need to be? X minus 5, because then it would be 1 over 1 minus x minus 5, which simplifies to 1 over 6 minus x. So that would be one way to do it. But if we do it the first way in the power series, it's still going to be powers of x. So it's still a Maclaurin series. It's still centered around 0. Whereas if we do it this way, we'd be replacing all the powers of x with powers of x minus 5. So it would now be a power series centered at 5. So it doesn't specify. So maybe power series is supposed to imply centered at 0. I'm not sure it does, though. I don't know. It's probably supposed to be centered at 0. So I would still call that a power series, but maybe that's wrong. Maybe power series implies 0. I don't know. So yeah, so we won't do it that way. We'll do it the top way. So here's the route. Let's move this down here. We're going to get from there to there. And then we'll the next thing we'll do is integrate with respect to x. And then that will get us what we're looking for, right? So we just have to get from there to there. So as we can see, if we do this, then we end up with 6 over 6 minus x. So what do we got to do to turn this into this? Well, we just got to turn that 6 into a -1. So we'll just multiply by, well, if we just want to turn a 6 into a 1, we'd be multiplying by 1/6. But since we want it to be negative, we'll multiply by -1/6, right? And that'll do it. Okay. So there's our path. There's our path that turns 1 over 1 minus x, the one that we do know the power series of. Oh, hold on. Did I forget to there we go. We'll start with the one that we do know the power series of, which is this one. Oh my God, tell me I'm recording. Yes, I am. Okay, thank goodness. Okay, so we'll start with this one, and of course, we can have the sigma notation for that as well. N equals 0 to infinity of x to the n. So, okay, so step one, replace x with 1/6 x, 1/6 x, and that'll turn it into that. So easy peasy, replace x with 1/6 x, very easy. That's just x over 6. That's x over 6 squared. X over 6 squared. Now I'm writing it in full. Probably better to actually just write it like that. And so on. So of course that's in sigma notation. That's literally just replace x with 1/6 x. So you could write it like that, or if you wanted to, you could write it like as you can see, my sigmas are really getting hasty here. Let me try again. So yeah, you can write it that way too. Okay. Now we need to multiply by negative 1/6. Okay. So that's now negative 1/6 plus, or no, they're all negative now. Everybody's negative. This is now 6 times 6. This is now 6 times 6 times 6, right? So they all gain an additional 6 in the denominator, right? They all gain a negative sign and they all gain an extra 6 in the denominator. And so on. So, and they're all negative now. So if we do that just with the sigma notation, well, it's negative 1/6 times this entire thing. So if you want to, you can say it like this. You can say all the terms are negative, and also everybody has one more 6 than they did before. So you could say it like that as well. Question? No? Okay. So yeah, that's it so far. And then finally, the last thing we need to do to get from there back to natural log is to take the antiderivative. So we'll take the antiderivative. This will be negative x over 6. This will be negative x squared over 6 squared times 2. This will be negative x to the, x cubed over 6 cubed times 3, right? So I hope it's clear what I'm doing here, right? This term becomes this term. This term becomes this term. This term becomes this term, right? And so each time the power goes up by 1, and that new power appears in the denominator, right? That's how you integrate. And so I'll just keep going here. The next one would be x to the 4 over 4 times 6 to the 4. And so on. So we'll just we'll do the same thing here. We'll integrate. And again, the beauty is that you can literally just do it in sigma notation is what's so great about it. So it's literally just, integrate. So the powers of x go up by 1, and then we divide by that new power. Like that. So yeah. So there you go. There's the answer. And so I should add this important technical detail. When you are integrating, when you do integration as one of these manipulation steps, you must. Oh geez, did I do a huge? Oh no, okay, I'm all right. All right, never mind. Yeah, so when you do one of these integration steps, you must worry about the plus c. What is the correct plus c to get from here to its antiderivative, right? Maybe you need like a +5 or a +3 or whatever, and you can't tell because when you take the derivative, those all disappear. So you can tell. But since we worked out, that when we started with this, we took the derivative to find out that it was this, and then we went back up the other way to take the antiderivative, and it turned out to be exactly natural log of 6 minus x plus c. Well, the only way that these can be equal is if the c was actually 0. So turns out that the correct c for this was 0. That might seem kind of silly, kind of weird, kind of trivial. Sometimes when you do this, you'll end up with a different version of that. Like, for example, if you do, I'm not going to get all the details of this right, but just for the sake of argument, if you use secant squared, you take the derivative of that. It's like something like, I don't know, something like that or whatever. This is not exactly right. I forget exactly, but and then you go back the other way, you might actually get something different. And it might be like, well, wait a second, aren't these supposed to be the same? How's that possible? Well, it's because of the plus c. The plus c in this case is 1, because these two things are equal with the correct plus c. So yeah, so sometimes you don't get the same thing and you got to worry about the plus c. But in this case, that's not what happened. The plus c is 0, so we don't really have to worry about it.
But that was ln of 6 minus x plus 5, outside the parenthesis. Then you'd find out c was equal to 5.
Yes, yeah, and then you'd have to add like have to be this, and then if you really wanted ln of 6 minus x, then you'd have to put the negative 5 on the other side instead. But we don't have to worry about that because there is no z is 0 in this one, so it's whatever. Okay, let me get rid of all that. Okay, so there's our answer. So it turns out that in sigma notation, I hope Darren is still here and paying attention. Yes, because now we have a perfect opportunity for re-indexing. So as we have presented it, the power series is n plus 1 over n plus 1 times 6 to the n plus 1. Now look at all those n plus 1s. In fact, every time that n appears, we call it n plus 1. So that's totally legit. That's totally fine. This is a 100% correct answer. But for aesthetic purposes, it might be nicer to call it this instead. Right, boom. Wow, so much nicer, right? And that's totally the same thing, because here the first term was when you plug in 0. So you get 1 here, 1 here, and 1 here. And then the next term, when you plug in 1, you're going to get 2 here, and 2 here, and 2 here. So that's totally the same thing as just starting here, right? If the first term is 1, you get 1 here, 1 here, 1 here. And then the next term is 2, you get 2 here, 2 here, 2 here, right? So it's totally the same thing. It's just, you're calling the first term n equals 1 instead of n equals 2. And that works out so much nicer because the first term involves, 1s, not 2s, right? Or 1s, not 0s, I mean. So that's why it's nicer to probably call this the first term rather than trying to call it the 0 term and having to shift everything over by 1. So either of these answers is 100% acceptable. I will mark those both full credit, but I'm sure you can agree that the second one is aesthetically pleasing compared to the first. So yeah,
is there a general rule you use with that, John? Like if you have like one is an n minus 2, one's an n plus 3, to maybe get rid of the negatives or something? Like here, it was obvious they're all n plus 1, so that's obviously a good rule to jump right to that.
I mean, yeah, not really. I mean, yeah, only because they were all n plus 1 did I say it's a good idea to re-index. If one of them was an n plus 1, but the other one was like an n minus 1, then, a gain in one exponent will just be a loss in another exponent. So it's kind of whatever, like you can kind of do whatever you want. So yeah, so it's strictly aesthetic. It's really whatever. You don't have to do it at all. But in my opinion, it's best to make such an exchange only if they kind of all match up, and that way, when you make the exchange, they all simplify down. if it was like, if this one had been like a, +3 instead, well, then you wouldn't have been super, it wouldn't have been quite as nice. It still might have been worth doing, but it wouldn't have been quite as nice. Yeah. Okay. Awesome. All right. I'm glad that was helpful. Fantastic. Fantastic. I do not know if you need to handwrite the test. What did he say? He said something weird. I better pull it up on a different device so I'm not showing stuff I shouldn't be showing. Let me pull up his thing here. Oh wait, no, he emailed it, didn't he? I just wanted to see what he said exactly.
Yeah, it came out. I got an email, but I think it was like a Canvas. He sent it from Canvas to the email.
Well, that's weird because I got the email, but not the Canvas.
Yeah, well, it just says Canvas at the bottom, so I thought maybe. But yeah, it was at 12:15. He sent it. 12:14. He sent it.
Well, Ervin was just wondering, should it be handwritten? I don't know. Listen,
Do you have the email, John, that came in at 12:14?
Yeah, that's exactly right. Yeah. So it says there is a WebAssign component and a Canvas component. Both will be visible at 2. For the WebAssign component, log into WebAssign and complete the work no later than 3:15. So that part, I'm assuming, will be automatically graded, and I will not be grading that. I'm assuming, perhaps I'm wrong. For the Canvas component, write up your solution, scan and email them. Yeah, so he's suggesting that you handwrite it. But if you have another way, like if you're, writing it on like a tablet or something, or that's probably best. Typing it is probably, honestly, typing kind of sucks usually because you don't have all the symbols that you need, and so it just gets confusing when you try to like shoehorn it into yeah. So typing is so I would strongly recommend and prefer if you were to handwrite it and scan it, or even just take a picture.
Yeah, we don't know if the Canvas portion is the same or different from the WebAssign portion. Someone suggested it might be the handwritten part of the WebAssign, only because it's worth 25 points. It's posted it, but you can't see it. So this test 3 Canvas portion opens at 2 tomorrow and it's worth 25 points. So we didn't know what that meant.
I'm sorry, Aravinda, I don't understand. It sounds like he's saying write it, by hand on paper, and then take a picture or scan it and submit it to Canvas. I'm not sure what you mean by on whiteboard.
I think Aravinda mentioned, he was talking about the whiteboard on her tablet, which I think you can do. If you can publish it to PDF, Aravinda, then you should be able to submit a PDF in any format.
Yeah, for sure. If you can, write it on a tablet or whatever, you can, submit PDFs or JPEGs of that. That's totally fine. And again, I'm like 90% plus sure that I'm going to be the one grading, so that's certainly fine with me. And I can't imagine that he would have a problem with that. That's almost certainly completely fine. In fact, I'm going to tell you it's fine. If he has a problem with that, then you can blame me and I'll convince him otherwise, because that's definitely got to be fine. So yeah. Okay. We have 23 minutes remaining before I have to go. Is there anything else I can help you guys with? I was kind of expecting more people to come, honestly. A lot more people came a couple weeks ago. I'm surprised it didn't become more for the test tomorrow. I had mostly Paris series representation, so I'm good. 10th question of homework 2, 100%. Yeah, if you can type that in the chat, that would be great. Or even just like explain what it is. It'll take me a minute to get to it. but I'll work on it if that's untenable. Oh, there we go. Fantastic. Thank you. Find the Taylor series for f, center at the given value of a. Assume that it has a power to expansion. Do not. Okay, great. Yeah, because that would be ridiculous. F of x equals what? Did that come out right? Ten over x. Oh, okay. At usf.edu. Oh, why am I doing that? I don't need to do that anymore. Okay, great. So, oh yeah, okay, thank you, Fahad. I almost called you F because the function is called F. Okay, so 10 over x, a equals -2. Right. So okay, so option 1 is to do the same thing as before. Start with the power series that we know, 1 over 1 minus x, and try to do things to it until you turn it into 10 over x. But that's going to be rather difficult. It might be easier to just go the Taylor series route, right? The Taylor series route says, if you want to find the Taylor series centered at a of this function, you simply need to figure out all the derivatives of f and plug in that number a into all of them. Right, so that's what we got to figure out for f. And in this case, our a is -2. So this becomes all the derivatives of f when you plug in -2, and then the powers of x, it's now powers of x plus 2. Right? Man, hold on. I need a little something. 1 second. Oops. Unfortunately, my immune system has destroyed my body's ability to maintain the amount of sugar in my blood. So I have to manually regulate the amount of sugar in my blood or I die. So that's why sometimes I have to go grab a quick glass of orange juice. Okay. Right. So fortunately, our function here it's actually not so bad to take a bunch of derivatives, right? Let's go ahead and get on it, and perhaps we'll see a pattern. So the first derivative, right? So that's going to be -10 x to the -2, right? I hope you can see that, right? We it's just simply power rule, right? The next derivative, the second derivative. I don't need this to be up anymore. I can put it down here. The next derivative. Well, you just bring the power down again. So it's going to be -2 times that. So it's 20 times x to the -3. And then the next derivative. Next derivative is -60. Next derivative is +240. There we go. And so on. So can you spot a pattern to what exactly is going on here? Let's see, what the hell would that be? -1200. Right? So what was really going on here? Well, really, we started with 10 times x to the -1, right? And then when we took the derivative, it was 10 times -1, x to the -2. And then it was 10 times -1 times -2 times x to the -3. And then 10 times -1 times -2 times -3 times x to the -4, right? So yeah, 10 times -1 times -2 times -3 times -4 times x to the -5, and so on. So what I'm getting at is, I'm trying to write it out in a way that it's clear to see what the pattern is. Because we're going to need to give a description of the nth derivative. Well, it's going to be 10 times -1 times -2 times -3 times -4 times -5, and it's going to keep going all the way until what exactly? So let's take a look. So this one was the fifth derivative, and it went all the way down till -5, right? And then the power was 1 beyond that. So it's probably a pretty good guess to say that the whoa, that was weird. Hold on, go back. Probably a pretty good guess to say that the nth derivative is going to go all the way out to -n. And then the power is just going to be -n and 1 lower than that, right? So it's probably a pretty good guess to say that that's the deal with the nth derivative. So can we simplify this at all, right? Well, notice how with all these negatives, right, each time we're multiplying by another negative number, notice how that the effect of that was basically making it alternating, right? Positive, negative, positive, negative, positive, negative, right? So we could accomplish that part of it, perhaps with a -1 to the n, right? Hopefully, does that actually work? If it's odd, it's negative. If it's even, it's positive. Yeah, so that's perfect, right? That'll take care of the negative portion, the negative positive portion. There's also this times 10, which was there from the very beginning. And then, like in the case of 5, right, we had 1 times 2 times 3 times 4 times 5. So in other words, that's 5 factorial if you get rid of the negatives, which we already did. And here we have 1 times 2 times 3 times 4 times 5 times blah, 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 times n. So that's n factorial. So I can say that the expression for this would have to be n factorial times x to the -n minus 1. Let's move this over a little bit. That was terrible. How did I end up all the way zoomed out again? Are you kidding me? I keep trying to zoom in so I have space, but it keeps messing me up. So yeah, so I hope you can see how this is the pattern, right? For all of these derivatives, right? There's a nice pattern that's easy to, it's kind of, unlike some derivatives where it just blows up in complexity with each derivative. This time it's like not so bad. Like, you can kind of see what's happening layer by layer, and then you can see what's happening even in the nth layer. You can kind of write it as an expression of n, right? You can say, I can say based on this pattern that the 27th derivative was going to be -1 to the 27, so that would be -1 times 10 times 27 factorial times x to the -28, right? So I can follow the pattern to tell you what the deal is all the way down there. And so naturally then what we need though is f of n at -2, which is super easy to figure out at this point. Simply, you literally just plug in -2 into that. Boom. Easy peasy. Okay. So that means that our Taylor series centered at -2 so it's the nth derivative at -2 divided by n factorial times x plus 2 to the n, right? Well, fortunately, we just produced a thing for that, right? We just produced an expression for that. So let me erase that and replace it with that expression. It's -1 to the n times 10 times n factorial times -2 to the, oh geez. All right, we got a little little compressed there, but that's okay. So now we can do a couple dramatic simplifications. One simplification we can do is these n factorials cancel each other out. So that's lovely. So it's the sum from n equals 0 to infinity. So now there's nothing in the denominator, so I won't even write the denominator. I'll put this 10 out front here. And then now we have these two things going on here. -1 to the n times -2 to the -n minus 1. So that is the answer. That is technically the answer right there. Technically, even this was the answer. You can stop right there, but you can simplify it dramatically, right? And you first of all, you can cancel those factorials. And in fact, there's still a little bit of simplification that we can do. We can simplify this a little bit further. The fact that this is a negative number to the n and this is a negative number to the n, those two negatives, we can work with that. Let's do that on the side here, actually. So it's -1 to the n and -2 to the -n minus 1. So here's what we can do with that. -2 is really -1 times 2. So that means we can distribute that exponent over that multiplication like this. And the reason that's useful is because now these are both -1s to a power. And as I'm sure you know, if you multiply, this many -1s together times this many -1s together, the powers just add. And that's absolutely gorgeous to add these together because positive n and negative n cancel each other out. So it's -1. And -1 to the -1 is simply -1, right? -1 to the -1, right? Of course, what that means is 1 over -1 to the positive 1, which is 1 over -1, which is -1, right? So there you go. So yeah. So there you go. So that whole thing just became dramatically simpler. It is simply -1 times that entire thing. It is simply I'll combine it with the 10. It's -10 times +2 to the -n minus 1. Oh, that was supposed to say n. Times x plus 2 to the n. And there you have it. So technically, this here was the right answer, but you can simplify it quite a lot. This is the simplified correct answer. And there you have it. That is the power series for 10 over x centered at -2. Oh, there's me. Oh. Yeah. Did that make sense? This whole process here, right? So the process was, take a bunch of derivatives and then try and figure out the pattern. Write that pattern as an expression of n. Plug in -2. And then pop that in to your Taylor series formula. Pop that into your Taylor series formula, and then simplify. And boom, there's your power series. Let's actually give that a test as well. So here's what we're trying to mimic with a infinite polynomial, and that infinite polynomial is -10 times 2 to the -n minus. Oh, come on, dude, that's so annoying. -n minus 1 x plus 2 to the n. And then b is just the thing that I have for a big number. So I'd say 20 terms or so. And there you go. So you can see how that totally matches up, at least on a certain interval, on the interval of convergence, right? So it is centered around, so let's call this F, because it is called F. And it's centered around -2, that point there, right? So at that point there, they are perfectly equal. And in an interval around that, they are perfectly equal. But once you go a little too far, then they stop being equal, right? So, yeah. Okay, I hope that makes sense. What do you think, Aravinda? Okay, sweet. All right, cool. All right. All right. So it's 7 o'clock. I'm afraid that's all we have time for. So yeah, so nice working with you guys. Good luck on the exam tomorrow. I will upload this straight away. Okay. Good night, everybody. Good luck on the exam. Bye-bye. Wait, is Jenna's not even here. That's weird.